Good morning, students. I, Jeevan Kumar Pandey, welcome you all to the online classes in science for standard 9th. Sorry, for standard 10th. Students, there had been some discussion on this particular chapter of electricity. Some topics have been covered. So, before covering further topics, I would like to briefly recapitulate what had already been discussed with you. The first topic that was discussed was electric current. We denote it by the symbol I, and we define it as rate of a flow of charge. Because these things have already been discussed, I will not give their definitions, etc. I hope you have already written them in your notebook. So it is defined as a rate of flow of charge or charge flowing per unit time. So we define it like this: I is equal to Q upon T. The SI unit for charge, that is Q, is coulomb, and for time the SI unit is second. Therefore the SI unit of current is coulomb per second. This unit is also given another name that we call as ampere. So we write 1 ampere is equal to 1 coulomb per second. Is it clear, students? So this is about electric current. In electric circuit, one query that is often asked, because you have covered some of the topics, that's why I am discussing this particular query, that why many students they ask why direction of current is taken opposite to direction of flow of electrons. And this question they generally put in the form of a circuit. Suppose we have some resistance R connected to some source of battery. What is asked by the students is that the direction of current is like so, but in this circuit the electrons are flowing in opposite direction. So current is flowing in this direction, that is in clockwise sense. In this particular figure, electrons have direction in opposite sense. Why is this so? See, this question doesn't have any answer. Nobody can answer why, but everybody can tell you it is like that. Now what I mean saying so is that it is a matter of convention, students. Actually, it is just a matter of convention that we say that by convention, direction of current is along the direction of flow of positive charge. Now nobody can answer you why. For example, in your number line, suppose this is origin. To the right of origin, by convention we take quantities as positive, plus 1, plus 2, plus 3. And to the left of origin we take minus 1, minus 2, minus 3. It is a matter of choice and is not based on reasoning. So if somebody wants, they can choose right direction as negative. They can put after origin minus 1, minus 2, minus 3, and before origin to the left they can put plus 1, plus 2, plus 3. There is no harm in that, and it will not affect much of the physical problems. But it is just a matter of convention. In this, while dealing with this particular current, it is widely accepted convention that we should choose current direction to be that one where a positive charge would tend to flow. Now in this circuit, this cell drives current due to flow of electrons in this particular wire. Now these are connecting wires. In the connecting wires, the charge that move are the free electrons. So those free electrons are negatively charged. They are considered to be negative. Again, if somebody asks why is electron negatively charged and why is proton positively charged, again nobody can answer why. It is just a matter of convention. Electron was initially given a charge negative and proton is given positive. Remember students, this does not mean that charge on electron is less than 0 and charge on proton is greater than 0. No. We know that charges are of two types and these two types are different. Like charges repel, unlike charges attract. You know these things. So because the charges are of two types, one of the types have been assigned minus sign, one of the types has been assigned positive sign. Now out of these two, one of them we have to choose as negative. So it could have been proton, it could have been electron. If proton would have been chosen to have a negative charge and electron would have been chosen to be positive charge, then this question would not have arisen. Because in that case, if electrons were positive charge, direction of current and direction of electron would be same. So it was an unfortunate decision to use the convention that electrons have negative charge and protons have positive charge. Because of this particular convention, this result arises that current we choose in the direction of opposite to the direction of flow of electrons. Is it clear, students? So remember, it's just a matter of convention. Convention means it's a matter of choice. So the direction of current is taken as the direction of flow of positive charge. In an electric circuit, the connecting wires, they carry current due to flow of negatively charged electrons. Now if positive charge would move towards right, it means negative charge would move towards left. Direction of current is along the direction of flow of positive charge. That means it must be opposite to the direction of flow of negative charge. So you can write the answer in your own words. I just wanted to discuss this particular query. After electric current, the next topic which we have read is potential difference. The symbol for potential difference, sometimes I might write delta V, but in your textbook they have used V as the symbol for potential difference. This has already been discussed with you. Let me revise again. What is the meaning of potential difference? At least you know, students, that charges, they exert force on each other. Suppose there are some charges here. You don't know what kind of charges are they. They may be positive, they may be negative. And there is a person A. Name of this person is A. And he has been assigned one task that he has to take 1 coulomb charge. Coulomb, you should know, it is the assignment for charge. He has been asked to do one task of carrying 1 coulomb of charge from this particular point P to this particular point Q. Is it clear? So he has been given an assignment to take 1 coulomb of charge in his pocket or in his hand and move from point P to point Q. Now when he carries this 1 coulomb charge with him and tries to come, now here I told there are some charges. Suppose we take positive charges. These positive charges would repel this particular charge of 1 coulomb, and if they are negative, they will attract. So this person will have to exert an equal and opposite force. Suppose it exerts, the person when he comes at this particular point, he is having that charge. Suppose this system of charges, they exert a force like so. If the person wants to stand here against this force, this person has to apply force in opposite direction. Then only these two forces will balance. So in bringing this charge from this point to this point, this person is applying some force and there is some displacement from P to Q. That means he will do some work. In standard 9th we have read about work. Work done is force times displacement. My point is, in carrying a charge of 1 coulomb from one point to other point, this person will do some work. Let that work be W. What is W? W is the work done by the external agent in moving or carrying charge of 1 coulomb from point P to Q. So there are 2 points P and Q. In carrying a charge of 1 coulomb from P to Q, the person does how much work? He does some work W. Then the potential difference between the 2 points, V is equal to potential difference between P and Q. It will be equal to W. Now suppose the person is not bringing 1 coulomb charge. This is by definition. Okay, this is the definition for potential difference. Potential difference between 2 points is defined as the work done by external agent in bringing 1 coulomb charge from, so you must have written these definitions in your copy, students, one point to another. This is the definition for potential difference. Now instead of bringing 1 coulomb, he might bring 2 coulomb, he might bring 3 coulomb. In general, suppose he takes charge Q. He takes charge Q from this point to this point, from point P to Q. And in bringing charge Q, suppose the work done is W. So W is the work done in moving charge Q from one point P to other point Q. Then V will not be equal to W. Why? Because W is the amount of work which the person does in shifting charge Q from one point to other. So for bringing charge Q, if the work done is W, then for bringing 1 coulomb charge, unit charge, how much work will be done? If cost of 2 mangoes is rupees 10, cost of 1 mango is 10 by 2, that is 5, unitary method, as simple as that. For taking charge Q, work done is W. For taking unit charge, work done will be W upon Q. So in this case, the potential difference will be W upon Q. That's it. This is the concept of potential difference. And by cross multiplication, you can write W is equal to Q times V. Now this relation is very, very important. So I would like to write this in words also. Work done by an external agent in carrying a charge Q from one point to other is equal to the product of charge and potential difference between those 2 points. Very, very important. Now this potential difference between 2 points, we have defined V as W by Q. So you can see, students, that if V is W by Q, W SI unit is joule, charge SI unit is coulomb. For V, the SI unit should be joule per coulomb. So SI unit of potential difference, which we write as V, is joule per coulomb. Now this joule per coulomb can also be written as volt. This is also called as volt, whose symbol is V. See these two V's. This V is the symbol for potential difference. This V is the symbol for its unit that we write as volt. There is a question based on this idea that potential difference between 2 points, suppose it is given as 1 volt. Then what is the meaning of this statement? So we know potential difference between 2 points is defined as W upon Q. It is defined as the work done in bringing unit charge from one point to another. It is given as how much? 1 volt. 1 volt means what? 1 joule per coulomb. And 1 joule per coulomb I can write as 1 joule by 1 coulomb. Any doubt, students? V is given as 1 volt. Volt we have seen, joule per coulomb, 1 joule per 1 coulomb. So your W is 1 joule and your Q is 1 coulomb. That is the meaning of this particular statement. So what should be the answer? It means how much work is done? 1 joule of work is done in moving 1 coulomb charge is 1 coulomb from one point to another. Suppose the question, so this is the answer to this particular question. Instead of 1 volt, suppose it is written 10 volts. How would your answer change? Same thing, V is equal to W by Q. Instead of 1, you will write 10 volts. 10 volts is nothing but 10 joules per coulomb. So this will be 10 joules upon 1 coulomb. So you can write this answer that work should be 10 joule, charge should be 1 coulomb. That means 10 joules of work would be done to move the charge of 1 coulomb from one point to another. See, you can put this answer in many forms. Somebody can write, so 10 joules per coulomb, you have written 10 joule by 1 coulomb. Somebody might write it as 1 joule upon 0.1 coulomb. Is it right or wrong? Of course correct, no problem in that. Because 1 by 0.1 will become 10 joule per coulomb. Can we write this answer like this? That potential difference between 2 points is 10 volt. This statement means that 1 joule of work is done in moving or bringing 0.1 coulomb charge from one point to the other. Answer is of course yes. No problem in that. So it's a matter of your choice what you wish to write, but generally it's a standard definition, because in the definition for potential difference we are bringing 1 coulomb of charge. It's better to give this definition, but no harm. I will happily receive this answer if somebody writes 1 joule of work is done in moving 0.1 coulomb charge from one point to another. So this is the meaning of potential difference. Another question based on this, suppose I give you, suppose there is a charge of 1 microcoulomb. Now if you don't know this symbol mu stands for micro, and micro means 10 to the power minus 6. I hope you know this. This charge is moved from point A to point B, between which the potential difference is given as 5 volt. I am not writing the language. So there is a point charge of value of 1 microcoulomb. It is moved from point A to point B. The potential difference between these 2 points is given as 5 volt. You have to find the work done by the external agent in moving the charge from A to B. Please frame the question yourself, put in your own words, then write the answer. So its answer will be how much? Work done. Which formula will we use? Charge into potential difference. Because you know V is W by Q, so W we can write as Q times V. The work done is charge into potential difference. Charge is 1 microcoulomb, that is 10 to the power minus 6 coulomb, and potential difference is 5 volt. So that is the answer, and its unit work as unit is what? Joule. So answer will be 5 times 10 to the power minus 6 joules. Is that okay? The next topic that had been discussed with you was Ohm's law. So let me briefly recapitulate this also. This is very important law in this particular chapter. So if there is some wire, metallic wire, and through that wire there is some current I, then this law says if you choose any 2 points on this wire, say A and B, and if you write V as potential difference between points A and B, so this we can write as VA minus VB. When I say potential difference, that is difference in the potentials at points A and B. So VA minus VB is our V. Ohm's law says that the potential difference between these 2 points on a metallic wire, so what is this line? This is representing a metallic wire. Potential difference between 2 points on the metallic wire is directly proportional to the current flowing through that particular wire. This means if this current increases, the potential difference between 2 points will increase in the same ratio, in the same proportion. And therefore we write V is equal to I times some constant. That constant, you know, we write it as R, and R we call it as resistance. Now there is some doubt amongst the students in this particular treatment of Ohm's law. Statements of Ohm's law, I know you have written in your notebook. Please have thorough revision of that. Sometimes the query that is often asked is this, that in some text they write the current flowing through a conductor is directly proportional to potential difference applied across its ends, provided temperature, other physical parameters remain constant. So there we should write I proportional to V. The query that is often asked, that if I proportional to V, then why don't we write I is equal to that constant R times V? And if we write this, and if we assume this to be correct, then both of them give reverse relations. See, this part is correct, no problem. Depending upon the situation of the experiment, you can have a setup where I is proportional to V. You can change voltage, you can change potential difference, and then current will change. For example, I can have a resistance and I can have a variable voltage source. I can increase this voltage. If you increase this voltage, you will find the current in the circuit will also increase. Current you can measure using ammeter. This is but wrong. Why? For a simple reason, that if I write y is equal to 2x, I cannot write x is equal to 2y. Can you? Here you will say, no sir, how is this possible? The same answer applies for this. If you are writing y is equal to 2x, x must be 1 by 2y. Here we can write y proportional to x, and that proportionality constant is 2. Here we will write x proportional to y, but the proportionality constant is not 2, it is 1 by 2. So here the proportionality constant is 2 in this case, and here the proportionality constant is reciprocal of that, that is 1 by 2. This same thing has to be applied in this particular context. When V proportional to I, you have used one constant, that is proportionality constant, that is R. When you write I proportional to V, the proportionality constant cannot be R, it has to be reciprocal, just as in this case. Instead of R, what will you write? You will write 1 by R, or this becomes V upon R. So I is equal to V by R, so V will be equal to IR. It will give you same result. Graph of Ohm's law, students, you know it is a straight line. Now here the graph can be drawn in two ways. Could you see what is the difference in these two graphs? The difference is in the axis. This is V versus I graph. What does this mean? Here it means that in the experiment, current is changed. We change current, and because of changing current, potential difference is changing, which we are measuring. So current is changed and changing potential difference is measured or observed. Here it is the opposite thing. Here voltage is changed. We change the voltage or the potential difference, and change in current is observed. Here we change current, because of which voltage changes. Here we change voltage or potential difference, because of which current changes. So here we say V depends upon I, and here we say I depends upon V. Students, if you remember in class 9th, you must have been taught about slope of a graph. Slope of this graph, if you see, if you choose 2 points, then the way that you have to find slope would be to drop from these 2 points perpendiculars on both the coordinate axes, like so. So suppose this point is B, this point is C, this point is like so, A, B and C. Then slope is tan of this angle, that is tan of this angle, that is perpendicular upon base. So it is AC upon BC. Now AC is what? AC measures the change in potential. It is potential difference. And BC measures change in current. So it is delta V upon delta I. See, AC represents voltage, you can remember. BC represents current, you can remember. Now Ohm's law says V is equal to IR. So what is our V by I? V by I will become equal to R. So if this graph is given, then its slope will give you R. But if such a graph is given where V is along the base axis and I depends upon V, then the slope will give you what? Slope will give you perpendicular by base. What is perpendicular? Perpendicular is this, that is I, and base is this, that is V. So slope in this case will be, here this was delta V, this was delta I. It is opposite here. Here it was delta V by delta I, here it will be delta I upon delta V, or I upon V. Now from this equation you can see V is equal to IR. So I upon V will be how much? 1 upon R. So based on this I can give you two questions like this. Suppose we have VI graphs. V is here, I is here. And there are two graphs drawn for two different metals A and B. And you are asked to compare resistance of A and B. Now you see, this graph is V versus I. So V depends upon I. So it is this one. For this slope gives R. Slope is equal to R. Now you compare the slopes of A and B. Out of A and B, B makes a smaller angle with I axis. A makes larger angle with I axis. Or otherwise you can think of this fact that if you sit here and if you sit here, in which of the two cases you will slip faster? Of course this one. That means this has greater slope. So we say that slope of A is greater than slope of B. But what does slope give? Slope gives resistance. So this implies resistance of metal A is greater than resistance of metal B. Same kind of graph if it is given like this. Instead of V versus I, if it is I versus V, and similar figure, this is A, this is B. Then in this case you should remember, students, slope is equal to how much we have discussed? Is equal to 1 by R. So don't try to memorize, just to see. Slope in this case will be I by V. Slope is here V by I, here it will be I by V. So I by V will be how much? 1 by R. So slope is equal to 1 by R. Now out of A and B, whose slope is more? Slope of A is more. So we'll write here that slope of curve A is greater than slope of curve B. But slope gives resistance, reciprocal of resistance. Instead of slope of A, I can write 1 by R of A will be greater than 1 by resistance of B. Now see, students, 2 is smaller than 3. Any doubt in this? No, of course. But when you take reciprocal, 1 by 2 and 1 by 3, when you compare, the sign changes. 1 by 2 is 0.5 and 1 by 3 is how much? 0.6 something. Sorry, 1 by 3 is 0.3 something, 0.33 will get. So 0.5 is greater than 0.3. So 2 is less than 3, but 1 by 2 is greater than 1 by 3. Same thing apply here. 1 by RA is greater than 1 by RB. This implies RA will be smaller than RB. You compare the answers in these two cases. Yes, this is RB. Here RA was greater than RB, but here RA is less than RB. Why it is happening? Because the axes are changed in this particular problem. Next topic that we had discussed, you have been taught, are the factors that affect resistance. So let us quickly see what are the factors. First one is length. Next one is area of cross section. Now let me modify this topic, This is factors affecting resistance of metallic wire. Metallic wire, conducting wire. For that, these are the factors. Then we have nature of material, of course, and there are some other physical factors like temperature. These are the factors affecting resistance of a wire. Let's see one by one. Length, you must have been taught that resistance for a metallic wire is directly proportional to length, and it is inversely proportional to area of cross section. I will not discuss much about this. And it depends upon nature of material. For example, copper, for a given material, for a material of given shape, size, length, etc., copper will have lesser resistance than iron because they are of different materials. And then temperature. For metallic wires, resistance increases with increase in temperature. If you raise the temperature, the resistance will be more, and if you reduce the temperature, the resistance will be less. In fact, this resistance is known to obey a relation like this: RT is equal to RT naught 1 plus alpha T minus T naught. What is RT naught? What is RT? What is alpha? RT naught is the resistance of the metal wire at temperature T naught. RT is the resistance at a higher temperature T. So T naught and T are the temperatures, and at these temperatures the value of resistance are RT naught and RT, and alpha is a constant. Just to remember its name, it is referred to as coefficient of resistance, temperature coefficient of resistance. So it clearly indicates that if you increase the temperature, then resistance will also rise. Now we are in this particular chapter more interested in these two relations. So R proportional to L, R proportional to 1 by A, these two relations can be combined to give you R proportional to L upon A. And if you remove the proportionality symbol, then you have to use some proportionality constant. That proportionality constant you must know, that is rho. And what is rho? Rho is referred to as resistivity. It is important to note that resistivity does not depend upon length, it does not depend upon area of cross section, it does not depend upon shape and size of the material. It depends upon these two factors. If I write factors affecting resistivity, then you will have only two answers. Factors affecting resistivity are these two: nature of the material, copper has lesser resistivity than iron. Then second one, temperature. If temperature changes, resistance changes. If resistance changes, resistivity will also change. So in brief, I tried to recall what has been discussed. So I have mentioned that in a note that resistivity of any metallic conductor, rho, it does not depend upon length or area of cross section or other physical dimensions of the metallic conductor. Is it clear, students? Okay. Next, students, please note down these homeworks. You might have done these homeworks earlier also, but it will be better option for you to revise it again. NCERT, the examples which are given in the textbook, 5 examples I am giving, I'll give you 6 examples, 12.1 to 12.6. So they are simple examples, and you must have done them earlier also, you must have been taught also, these must have been discussed. So these examples are solved in the books. You please solve it yourself in your copy notebook, and then blue ink questions on page number 209. Question 1 to question 5 will also be your homework. In this blue ink question, 5 questions are there. I will discuss one of them. Question number 2. Question number 2, it is asked, just I am reading the question for you. Will current flow more easily through a thick wire or a thin wire of same material when connected to the same source? And they are asking then why. I am repeating the question. Will current flow more easily through a thick wire or a thin wire? Suppose I have a thin wire or thick wire and I have a thin wire, and it is asked, out of these two wires, when you connect them to a voltage source means battery, like this. Same voltage source V. Then it is asked, in which of the two cases current will be more. So what is the difference in these two? So it is given thin and thick wire of same length. Length is L, here also length will be L. Here suppose area of cross section is A, here area of cross section is A dash. And it is given that this is thick wire, so area of cross section A is greater than A dash. Now length is same. Now we know resistance of a conductor is given by the formula rho L by A. Both these conductors are of same material. That's why their rho is same. Both have same length, so they have same L, but their area of cross sections are different. If rho and L are fixed, so we'll write for fixed values of rho and L, we can write R proportional to 1 by A. That means resistance is inversely proportional to area of cross section. So if A is more, R will be less, and so on. So out of these two, which will have less resistance? This one. So this implies thick wire, the one which is thick, because its A is more, R will be less. So thick wire has low resistance, and you know the definition for resistance, that if resistance is less means opposition to current is less. If this implies current will be more. So you can put in your own words. So in the thicker wire, because area of cross section is more, its resistance will become less, and because it has a low resistance, the current will be more in the thicker wire. So students, I will stop here. If you have any queries, you can put in the query link. But I suggest you to read the contents once again properly, and in the next class we will discuss series and parallel combination of resistors. So till then, read well, stay at home, use your time, utilize your time judiciously, and whatever queries are there, please share with your friends, and you can consult of course through the query link. I wish you all the very best. Read well. Thank you.